So, in this chapter, we started with just basics of what is a function. And if you'll recall that in order to determine if something is a function, that it has to have a one-to-one relationship. And so if it asks something like a mapping diagram, remember that is just where you are listing your domain and your range, numeric order. So we're going to list it least to greatest for each of these. And then we would draw an arrow from each of these. So 3 goes to 2, 4 goes to 7, 3 goes to 1, -2 to 4, and -1 to 8. And you can see that no, this is not a function. If I ask why it's not a function, you would tell me that you have two y values for x equals 3, which causes a problem. The other way to determine if something is a function is just the vertical line test, which is this next one. And so vertical line test, if it crosses a function more than one time at any spot, it is not a function. From there, we move to how to determine domain. And so the domain of a function is really you're going to assume all x's work unless something causes a problem. The first thing that can cause a problem is the denominator. And so for just domain, don't think about discontinuities just yet. For just domain, we're just going to say where is the denominator a problem? So you want to factor that denominator, and then you want to see what makes each of these 0. So for this first one, -1 would be a problem, and this second one, a +1 would be a problem. And so for set notation, it's really simple. You're just going to say it can be x such that x does not equal those two numbers. And as long as it does not equal those two numbers, you're good. For interval notation, you want to start at -infinity and you want to say, well, I can go all the way up to +infinity except for these two numbers. So you want to stop at each of those numbers and just kind of walk your way up to +infinity from there. And so that would be set notation or interval notation for something like this one here. If we look at the radical, radicals have a problem when they're negative. So everything else doesn't matter. We just care about that radical. And we want to say the radical can't be negative. Well, the way we say it can't be negative, it would be greater than or equal to 0. So just solve that. X has to be greater than or equal to 2. For set notation, you really have it right there. That is your set notation. For interval, if it's greater than or equal to 2, you're starting at 2 and you're going to infinity. Infinity is always open. If it's or equal to, it is closed. After just general function information, we moved into specific types of function, one being linear functions. And so just to recall, you need to know those slope formulas, which is just the subtraction of the y's over subtraction of the x's. You need to know your slope intercept form, y equals mx plus b. You also want to be able to use your point slope, where if you have a point and the slope, you can come up with your function. And in this case, that's what these are seeing. They have these 2 points. They want the slope intercept form of the line. So the first thing we have to do is we have to calculate our slope. And so as we calculate the slope here, we're just going to subtract our y's, subtract our x's. So -1/4 is going to be our slope here. And then we're just going to use either of those points with my point slope equation. So I'm going to say y minus my y value here equals mx minus my x value here. And at this point, we're just simplifying. Distribute, combine any like terms, and then you're going to move that one to the other side. Move that over. So in slope-intercept form, we have negative 1/4 x minus 7/4. When we're graphing linear equations and it asks for our x-intercept, y-intercept, and slope, remember there are shortcuts when it comes to standard notation being ax plus by equals c. My x-intercept will be c over a, y will be c over b, slope will be negative a over b. And so you can jump right to your x-intercept, 6 over 4. We'll reduce that, of course. Y-intercept, we would say 6 over 3, and of course, reduce that. And then my slope, we would say negative a over b. You should also be able to write the slope-intercept form of the equations given a point and a line either parallel or perpendicular. You're going to use the same exact formula you did before, this point slope, and you will say y minus your y value equals. And then for parallel lines, you are going to use the slope exactly the way it's given to you in the line that they want you parallel, in this case being a 3, and finish it out x minus your 2. You will distribute and simplify those. And then for perpendicular, you're going to use the same exact formula, y minus your y value equals. But in this case, your m for this, you're going to take that m from the perpendicular function. You're going to flip it upside down. So instead of 3/4, 4/3, and then whatever the sign is, you're going to do the opposite. That was negative, we'll use a positive. So we're going to use 4/3 and then our x minus that 5. And again, you will simplify it with your distribution and moving that over with common denominators there. And so move that over and put it in slope-intercept form. Now, after linear equations, we moved into continuity. And so for continuity, you have functions like this piecewise function, where it gives you something, two different uh, definitions, one for less than 4, one for greater than 4. And really what you want to do is you want to plug those in. So we're going to plug a 4 into this one. That is your y value there. And then here, your y value is always 0. If those do not match, then you definitely have a discontinuity. For jump functions, if it is a greater than less than, or for piecewise rather, you're going to have a jump discontinuity. If they give you something like this, where it's just one number that they have pulled out, that is going to be a point. So, and then if they equal, if they were to equal, it would be continuous. And so for piecewise, you're really looking for, is it continuous or do they equal when I plug them into each piece of the piecewise function? And then you're going to determine if it is a jump or just a point that they pulled out. We could also look at other types of functions. You could have just a polynomial. Something like this is always going to be continuous. There's no denominators, there's no radicals, there's nothing that would cause a problem in this function. But anytime you have a rational, which is a fraction, then you are going to want to see if a denominator causes a problem. And you want to do this by factoring. And so you want to factor all your pieces because you have to classify the type of discontinuity. And so you're going to factor the top, and you're going to factor the bottom. And you can see that there are two problems in the denominator. You have a potential problem with this m plus 8. So if you had a negative 8 there, that would be a problem. And then you have a problem with this m minus 4. When m equals positive 4, you have a problem. And so now you should have to determine what type of problem. For the m minus 4, you could cancel it out. So that is a removable discontinuity, or we can also call it a point discontinuity. It'll look like just a hole in the graph. For the m plus 8, or where the negative 8 is, you cannot get rid of that. And so that is going to be an infinite discontinuity. This chapter also discussed translating graphs. And so you do need to know those parent functions. When you look at sketching a graph, the first thing you want to notice is what is the parent function and what would that look like standard. So recognize you have a cubic function, recognize that it would standardly look like that. And then how is it moving? Remember on the inside moves it left and right. The outside moves it up and down. And then your negatives will reflect it and your coefficients. So if the absolute value of your coefficient is bigger than 1, or if it's going to stretch it. And if it is less than 1, it is going to flatten it, so to speak. And so you do want to pay attention to um, those particular pieces as you graph. So when I look at this one, I'm going to say, well, on the inside is at -2. Remember, your original function is minus, so it looks like it's doing the opposite, but that vertex, so to speak, is going to move to the right. And then we do have a negative in front. And so that negative is actually going to flip it, and it's going to make it do something like that. So I would recommend then, once you figure out where that middle point is that we're shifting, pick some points. So I'm going to maybe pick a 0 over here, and I'm going to say, well, -2, if I plug in a 0, what happens there? And so I have a -2, and plugging in a 0 gives me a -8. That gives me 16. That's huge. So that goes off my graph. So I'm going to pick something a little smaller, and I'm going to say, well, let's do a 1. 1 minus 2 cubed, -2, -1 cubed. That's going to give me just 2. So if I plug in a 1, I get 2. And so I'm going to graph that 1, 2. And then I'll plug in a 3 and do the same thing. So I'm going to say -2, 3 minus 2, quantity cubed. 3 minus 2 is 1, 1 cubed is 1. And then times 2 is -2. So I know that if I plug in a 3, I get -2. And so I'm going to go to 3, and I'm going to plug in -2. And then you can see that my graph is going to do something like that. Kind of the reverse of that is if you are given a picture of the graph, and then they want you to define the function. And so again, the first thing you want to recognize is what your parent function looks like. In this case, this is the reciprocal function. Normally, this little crosshairs guy would be right here. So we see that it's shifted to the right 3 places. So we're going to take that original function, and on the inside, we're going to move it to the right. We also should recognize that my reciprocal function typically looks like this, and you can see it is flipped. So we want to put a negative in front there, which will give us our function for this graph. So from those parent functions, you should be able then to graph um, piecewise functions. You want to go through these and you want to say, well, I have a parabola, I have an absolute value. And so now I want to break my graph up into sections. And pretty much this is just two pieces. One is what it looks like uh, anywhere else on the graph except three. So when it is not three, it's going to be a parabola. So I want to go to that parabola. That parabola moves to the left. And I want to sketch that parabola. And that parabola looks like this, something like that. Except the problem is uh, the number three. So three, they don't want me to use the parabola. What do they want me to use at -3? Well, they want me to use this absolute value. So I'm literally just going to plug this in. So when the function input is -3, the output is +3. And so that means I am not here at -3. I'm actually here at -3. And so that's what this unusual piecewise function looks like. Now remember, you could have other ones on which we've done many examples where you split that graph up into, three sections, and maybe you have an absolute value function over here, and maybe you have a parabola somewhere in here, and you have to determine kind of what is happening to these functions. And so you could have any number of piecewise functions, just depending on what they give you and what you have to figure out. You're literally just doing pieces of the function. And then a more specific function that we did was quadratics. When we're graphing these, remember in standard form, this is asking for the axis of symmetry, which is -b/2a. The vertex, which is just that -b/2a, and then plug it in. And then the y-intercept, which is 0 and c. And remember, we have A, B, and C. For vertex form, which is the other one, we have A, H, and K. Remember, my axis is x equals h. My vertex is h, k. And my y-intercept is just 0. And then what happens when I plug it in? And then, of course, you can graph those as well. So quadratics we've done multiple times. Remember, you want to pay attention. If the A is positive, that's going to be up. If the A is negative, that is going to be down. And then the last thing we did was finding zeros. You can find zeros by factoring or by using the quadratic formula. And so if you are factoring, you want to make sure that you set it equal to 0 and solve from there. So if I were to do this one, 25r squared plus 5r minus 2 equals 0, I could solve by factoring or by quadratic formula. Same with 17. Again, before I start, I want to have it in standard form and equal to 0. And then from there, you can use the quadratic formula or factoring. Either one will work. One thing I do want to remind you of is we did direct variation and indirect, inverse, etc. So remember for those word problems that when you see directly varies, it's going to be the first term directly varies with k times the second term. Inverse is going to say that the first term inversely varies, so it's going to look like that. And remember, you can have squared or cubed. It could vary directly or inversely with either of those. And you are simply just plugging in the xy and solving for that k to then use that formula. And so all of those topics we've covered, you can go back and review the other videos as well.